Okay, so last question then was question 3, which is about satellites. So like I said, most of these questions, when you've got constants in there, they will give them to you. So you've got universal gravitational constant, and they've also given you the mass of the Earth. So just bear in mind that if they've given them to you, there is somewhere where you are going to need to use them during the questions. So the first bit talks about a satellite in a circular orbit, and it gives you the radius of the orbit. So we've got 7 times 10 to the 6 meters. It says, name the force that's keeping the satellite in this circular orbit and state the direction in which this force is acting. So a fairly easy one to start with. When we're looking at satellites orbiting around, it's going to be gravity that's keeping them there, and the direction is always towards the centre of the orbit. Okay, just be a little bit careful with that. I think some of you said towards the centre of the Earth. It doesn't actually necessarily tell you at this point that it's orbiting around the Earth. It just says it's in a circular orbit, and it tells you the orbit of rotation. The only place it's really mentioned Earth is up here, but it doesn't specifically say it's orbiting around Earth in the question. So again, just an achieved for that one, because it was relatively straightforward. So then carrying on with the gravitation for the rest of this question. Calculate the value of the acceleration due to Earth's gravity at this height above the Earth's surface. Write your answer to an appropriate number of significant figures. So we're looking for acceleration due to the Earth's gravity. So two things that should pop into our heads is whenever we're thinking about acceleration, force divided by mass. We also know, though, because we're talking about gravitation, that the force is equal to gmm over r squared. So if we pop these two equations together, we can think about putting this in terms of our mass. So if we do that, we've got mass on the bottom and mass on the top, so we end up with A being equal to gm over r squared. So the gravitational constant was given to us, mass of the Earth was given to us, and the radius that our satellite is travelling at, and don't forget that that's all squared, and if you put that into your calculator, I think you should get that value there. So you got an achieved for getting the right equations, so if you're talking about the right two equations and putting them together as we've done here, and then there was a merit for getting the actual correct answer. Significant figures should be 3 significant figures, so 8.14 are your 3 significant figures. There was an extra achieved, I think, for getting correct number of significant figures. Part C, calculate the speed of the satellite. So again, thinking about things orbiting, we're going to be thinking about circular motion. So if we think about circular motion, this is an equation that you're very familiar with from level 2, F equals mv squared over r. And again, we also know, though, that that force is equal to gmm over r squared. So we want to make velocity or speed the subject of these. So we can get rid of the m's and we get v squared over r is equal to gm over r squared. And then we can get rid of one of the r's, so b squared is equal to gm over r, or v is equal to the square root of gm over r. And again, you've got those two values, you've got your radius in there. I think if you put all that into your calculator, you end up with that for your speed. So combining the equations and getting to this point got you and then putting the values in and actually getting the answer out got you up to excellence. So I think once you got to this point, and the excellence was really, really straightforward. That question's really nice, easy excellence question. D for most of you is just being a little bit more specific about what you're actually writing. So explain why the astronaut in the satellite feels weightless while in orbit around the Earth. I think what a lot of you didn't really talk about was the support force and the idea that weight or the sensation of weight is caused by the support force acting up on our bodies. So if you've got something sitting on a surface, you're going to have the weight force acting downwards, and you're going to have some kind of support force. So because they're talking about weightlessness, so the weight sensation is caused by the upward support force on our bodies. So in space we've still got gravity, because they're not in outer space, so we've still got a gravity force acting on them, but the difference is here they're in free fall. So as the astronaut, it's not a spaceship, and the satellite, so as the astronaut and the satellite accelerate down at the same rate, there's no support force. And probably if you think back to level 2, you guys probably did that experiment where you went out to the elevator down at the other end of the school, and you probably took the bathroom scales down there and had a look at this, and the way your weight will change depending on which direction the elevator was going, and whether you were slowing down or speeding up. So, and you probably looked at this idea again when we did vertical circles. So if you've got your spaceship and your astronaut, and the spaceship is accelerating down and the person is also accelerating down, there's going to be no support force between them because they're both accelerating down at exactly the same rate, so you get no support force.